This interactive video summarizes a comprehensive research report prepared by a consortium of 15 research organizations, mostly universities, known as Quorum. Quorum was formed to manage research and educational programs related to renewable industrial materials, focusing on the environmental impact of the production, use, and disposal of wood and other bio-based materials. I'm Bruce Lipke. I'm a professor at the University of Washington, and I'm the current president of Quorum. You probably have noticed that over the last decade, there's been growing interest in environmental performance, and especially the impacts of forest management. I think it's a safe prediction that environmental pressures will continue to grow, moving right along the stages of processing to products, buildings, their use, and ultimate disposal. The environmental quality of residential buildings is of great importance, and in this report we use life cycle inventory and life cycle assessment methods to develop a database that can be used to assess environmental performance. We show how the manufacturing processes, materials, and building design impact performance, as well as identify ways to improve performance. Environmental measurements can raise emotions, so I'd like to start with what is needed to measure these things and what our objectives and methodology were. We'll also go into the scope of the Quorum Phase 1 study. We'll look at the environmental performance results from our study through building construction and then take it on through building use, maintenance, and disposal. Carbon pools are very important to forests, so we will look at carbon pools starting with the forest and taking it through the construction. Just before we conclude, we'll look at some opportunities for environmental improvement, and then I'll sum up with some take-home messages and just a few words on the scope of our Phase 2 research extensions. If you think about it in a picture, this picture should help. What we're about is to measure all the inputs and all the outputs of all of these stages of processing, starting with the measurements for the regeneration of the forest, the management of the forest, the production of the logs, production of products, not just wood products, including the production of steel and concrete and other materials that are extracted from the soil, the construction of the building, the maintenance of the building, and the use of the building. So our mission is to measure all of these inputs and outputs so we know what the full environmental performance spectrum is for the production of these products and the production of a building. Our study objective then is to develop a public database and models of environmental performance measures over the life cycle of wood products used in residential buildings. Why do we want this public database? Well, that's going to allow us to examine a range of management, product, and process alternatives so we can identify strategies to improve environmental performance. Now, Quorum's research protocols were very much in depth. We actually created Quorum as a nonprofit research corporation to get the full support of 15 research institutions, which we thought was the needed capacity to do this study. We developed a very comprehensive research plan. It involved some 22 different modules. Our first phase that we're reporting on today is just the first 6 modules. Quorum's research guidelines follow the LCI and LCI International Protocol of the ISO 14040 standards. All of our work has been reviewed by international LCI, LCA experts, both in preparation of the guidelines, halfway through the project, and in the completion of the project. A little bit more descriptive of the flow of information and the collection of information is provided by this flow diagram, where we're basically out to collect all of the inputs and all the outputs, starting with the forest management phase, which includes regeneration of the forest, through transportation, through raw material acquisition, harvesting, through product manufacturing, building construction, use and maintenance, and the final recycling and demolition of the building, transportation for all those stages. In the outputs, we're measuring all the different emissions in the fluids and solid waste. The useful life of a house is our primary product, but we do keep track of all the co-products, including the chips that go into paper making. So we're collecting data, and you can imagine there's a lot of data when you collect all these inputs and all these outputs for every stage of processing. Now, the output of the quorum study are these life cycle inventories. That's these measurements of all these inputs and outputs for forest harvesting and structural wood products. To reduce the magnitude of this data and make it more useful for an analysis standpoint, we develop what are called life cycle assessments by collecting those data into intermediate risk industries, such as the toxicity of air, air pollution, water pollution, energy consumption, global warming potential. These are the things that make it much easier to analyze how much performance progress we have and what our impacts are. We also keep track of carbon, tracking it from the forest and through wood products and into buildings. We've done a lot of sensitivity analysis on these LCI and LCA models. So basically we have the basis for a benefit cost analysis and the ability to identify opportunities for improvement. A couple of words on why these results are important. Basically, they provide benchmarks of environmental performance for forests, mills, and buildings that can be used to evaluate improved performance alternatives in terms of these indices. Including the ones I just mentioned, you can look at the bottom and you can see forest structure or health. The ones before that, it's very easy to make direct comparisons between different materials, wood, steel, whether they're coming from a regeneration of a renewable forest or whether they're coming from an extractive process. But we do measure forest structure, health, biodiversity, even though it's not directly comparable to the similar kind of problems that might be incurred by a non-renewable resource. So why are these results important also? Well, this life cycle inventory data and assessment can be used to establish fair and reasonable environmental standards. If you look at our results, you'll quickly conclude that guessing can't get you there. The quorum data will be used in a U.S. LCI database, which is being established for all primary processes. It's being managed by the Department of Energy's National Renewable Energy Lab, and it will include processes for steel and other materials that are properly reviewed the same way as our quorum data is reviewed. When we collected our environmental data, we basically did primary surveys for the forest harvest, wood products, manufacturing, and transportation phases. But for our secondary data for non-wood materials, electricity, fuels, and transportation, we basically used other models. The Athena model, designed in Canada, is designed specifically for architects to be able to easily design a building and get the life cycle inventory and analysis data for that building. And we also used the CIMAPRO program with the Franklin database to manage the data for our product data. So we ended up with input-output surveys conducted on some 20 product processing and housing life stages. We basically concentrated on the two major supply regions in the U.S., the Pacific Northwest wood production and the Southeast wood production. And for our representative buildings, we analyzed an Atlanta house as a representative for the warm climate and a Minneapolis house to represent a cold climate. Now, if you put all these things together, by this flow diagram, we kind of show the forest resources and harvesting up in the upper left-hand corner. We show all the processes of all of the building materials that we made out of wood. We show the construction stage for these two buildings, the building use and maintenance stage, and final disposal. When you cover this information all the way from the beginning to the end, we call it a cradle-to-grave analysis. We only look at the impacts for the processing of the materials. We tend to call it a product gate-to-gate analysis. Probably one of the more useful outputs we'll show is the cradle-to-construction analysis. That's where most of the impact is. So when we do our primary surveys of each one of these products, we actually collect this data at the unit process description level. That means sawing, drying, planing, and even energy production are separate processes. When we do the mill surveys, we do them at each one of these unit process levels. That way, if you want to change any one of these unit processes, you don't have to resurvey the whole mill. You can plug in the process. It gives you a better understanding of what's driving the impacts. We've collected all these non-wood inputs, energy by source, raw materials, We've collected all the emissions and solid waste outputs. That means we have a lot of yield and flow data following all the products and co-products. That means we have mass balances. If the mass balances between the input and output don't balance within 1 to 2%, we go collect more data or try to figure out what assumption went wrong. Usually it's going to be the amount of moisture assumed in a product rather than what it actually was. Using this data, then, we calculate what are known as unit factor estimates. That is, for every 1,000 square feet of plywood, we measure the amount of raw material required, the air, the water, the solid emissions, the energy, carbon, and all the other inputs and outputs associated with that unit of production. If you look at it in a data table, it looks like a lot of data. On the left, we start off with all of our inputs, starting with wood, the resins, the energy, the different sources of energy. On the right, we start out with our table of outputs. The bark, the products. Plywood being, in this case, our major product. There are a few co-products. Then we start with a list of air emissions. Actually, the air emissions table is probably twice as long as you see in this diagram. Then we go on to water emissions and solid waste. And so by the time we're through, we have a much larger table than this. That's a lot of data for one product when, in fact, we're going to use many products to produce a building. How do you get information out of this massive data? Well, here's a typical cross-section of this data, where we are looking at the total energy by stage of processing for each one of our major structural products. You can notice on the right-hand side, the green lumber uses very little energy. But we basically build buildings out of green lumber in the Douglas fir region in the Northwest. The minute you dry the material, such as our lumber kiln dried, you can see that the dominant source of energy is increased for product manufacturing, just for that drying stage. You get to our other products, LVL, plywood, glulam, you can see the impact of resins begins to appear. And for OSB, partially because it's wetter wood and has much higher resins, you see a substantially increased use of energy. In any case, all of these energy uses for these products will turn out to be quite a bit less than most of the more fossil-intensive substitute products. Even for those energy sources, the one thing that we don't show on that chart is that much of that energy can come from biomass. Burning hog fuel as a source of energy does not produce fossil emissions. It basically is essentially neutral from the emission standpoint. Since you grew the wood over a rotation, you harvested some of it for energy, and so there is no net change in carbon dioxide emissions. You can see that for the Pacific Northwest, we only generate about 60% of the energy from biomass. But if you look in the Southeast, you can see that some of our products are as high as 100%. The reality is we have plenty of low-grade residuals to be producing 100% biomass for most of these products. It doesn't happen because the price of alternative fuels, such as natural gas, are so low. So there are ways in which these biomass processes could increase. Now let's turn our attention to the life cycle assessment story, since we kind of sketched out how we collect all of this very detailed life cycle inventory data. We collect these we take the inventory data and reduce it to, first we collect all the energy as embodied energy. Then we go on to global warming, air emissions, water emissions, and we'll talk a little bit about how each one of these collected. But first let's look at a little bit more detail on the houses we designed to local code. Our Minneapolis house is a full 2-story house with a full basement. We designed both a wood and a steel framed house. They were both designed to the same R code. They essentially used vinyl siding on the outside, which is the dominant siding used in Minneapolis. Our representative Atlanta house is built single story as a slab on grade. Here we're showing both the wood frame with that vinyl siding and comparing it to a concrete block exterior with a stucco finish. Again, both designed to the same R code, although a much less restrictive R code than the Minneapolis house. If you look at the mass of materials that goes into that wood frame Minneapolis house, Might be shocking. It was certainly shocking to us. Wood is only 17% of the total materials. When we change that wood house to a steel framed house, we're only changing the framing, and only about 6% of that wood is moved over to the metal column. That is to say that the framing change that we're demonstrating in our design changes, going from wood to steel and wood to concrete, only shifts about 6% of the mass of the house. All the rest of the materials are still common. So when we look at our design differences and compare the Minneapolis wood house to the steel house, you can see that the steel versus wood differences basically is as simple as we've reduced 6 metric tons of wood and replaced it with about 6 metric tons of iron ore, plus metallurgical coal and some of the other energy-intensive elements that go into this making of steel. We do the same kind of comparison to the Atlanta house. It's even a little more dramatic because the Atlanta house basically still contains a wood structure inside the concrete block wall to house the insulation. So in this case, we only eliminate about 2 metric tons of wood fiber and replace it with about 2 metric tons of limestone. Yes, there's a lot of fine aggregate materials that are used for the concrete house, but we typically find them to be fairly inert and not having huge environmental impacts. So if we look at the energy consumption in Minneapolis, our 10 different energy sources, if you will, you can see that other than the feedstocks that go into producing the steel, it doesn't look like a huge difference between them. That's because so much of the building materials are actually common to both houses. Nevertheless, if you zoom in on where the products are changing, you can see here the total energy in our wood frame house goes from 646 gigajoules up to 759 for the steel house. That's a 17% increase, even though we only changed the mass of materials by about 6%. And when you look at the substance of the parts that aren't common, you can see that the wood frame house has a little bit of wood and insulation contributing to the energy. When you go over to the steel house, there's a substantial increase in both the energy to produce the steel and the energy to produce the wood. And the energy to produce the insulation. So while there's only a 17% increase in the total house level in the energy use, there's several 100% increase for those products that in fact are being substituted. If we look at the Atlanta story, it's much the same story. Fairly similar amounts of energy used from many of the sources, somewhat higher, of course, for those things that are feeding the concrete. And again, when you break it down and look at only those products that are being substituted or changed when we change from a wood frame to a concrete frame, you can see that most of this energy difference is in the rebar and the wood in the wood frame house. In this case, the insulation levels are the same, but what you do see is a substantial increase in the rebar and the block and mortar. And again, it's a several 100% increase in energy for those products that are actually being substituted when you change from wood frame to a concrete frame. We go on to our global warming potential index. We basically use EPA's formulas of what is the CO2 equivalence effects based upon carbon dioxide, nitrous oxides, and methane. We'll show you those details in a minute. When we look at air and water pollution indices, it's a little bit more difficult because even though we have different elements that are contributing to toxicity, they don't have the same contribution. If we look at the raw level of emissions to water, if you look at this chart, right down there in the middle to the bottom, you can see cyanide. It barely shows even a small increment on this chart, but it happens to be the most toxic. So when, in fact, we dilute it to a safe EPA standard, the cyanide coming from the steel is by far the most toxic element. The phenols coming from the wood are the most toxic element for the wood house, but they are, in fact, much less. So in this case, there's much higher toxicity in water coming from our steel frame house. We do the same kind of analysis for Atlanta, where while there's still some rebar in the concrete house, you can see that the toxicity coming from the cyanide and the toxicity coming from the phenols in the wood house are almost the same. They're insignificantly different. Finally, we come to solid waste, which we don't have to worry about weighting so much. We basically can add up the units in a mass sense. The difference here is in all the other profiles, manufacturing was by far the dominant contributor. In this case, the construction of the building is every bit as important as the manufacturing process. And in this case, steel produces 1% less to solid waste than the wood frame house does. Now, if we switch to volume as a better indicator, which is not the convention normally used for this kind of analysis, but it can be argued that volume might in some cases be a better indicator, then of course this number would get a little bit worse for wood than is shown here. In the case of Atlanta, you see a substantial amount of solid waste coming from the construction, and the concrete block is fairly inefficient in the sense of waste at the site, resulting in about 51% greater mass going into the solid waste than from a wood house. So with these, we can summarize the performance industries for the Minneapolis house as we've done in this chart, showing that the embodied energy for the steel house is 17% more use of energy than the wood house. The global warming is up some 26%, air emissions some 14%, usually not quite as severe as the global warming potential. Water emissions are quite large, then the solid waste is slightly better for the steel house. However, since most of those materials were common, if we zoom in on a subassembly, in this case we picked the floor and the roof. Now the floor in this case is where the substantial change is taking place. The roof is actually common to both of these houses. Now you can see that there's some 67% more energy consumed in the floor and the roof, substantially more global warming and air emissions, not much change in the solid waste. If we go to our Atlanta house, you can see the embodied energy being 16% more, global warming some 31% more. Generally with the concrete structures, you get a somewhat enhanced impact in global warming because of the calcification process in making cement. Air emissions 23%, and as we saw earlier, the solid waste is some 51%. In this case, we'll compare the above-grade wall to the total unit because all of the substitution is taking place in this above-grade wall by replacing the wood framing and exterior with a concrete block structure. And you can see that, again, we have much larger increases when you concentrate on the subassembly where the substitution is taking place. Now, with this kind of a summary for these stages of processing up through the construction, we can now going to go on and see what the relative sizes of the building life cycle stages are, including maintenance and use and demolition. As you can see from this chart, the energy from maintenance is about 10% of the energy required to build the structure. Not only that, of course, that energy is largely distributed over many years, the full 75-year life of a house or more. So it doesn't happen instantly. It doesn't happen at the same time as the energy required in building the structure. Energy for demolition is quite small and somewhat higher for the concrete, but not very significant. Now, if you go down to the bottom part of the page, you see the heating and cooling energy. This is where the big difference is, because when you accumulate the heating and cooling energy over the 75-year life of the house, you'll find out it's almost 10 times what the energy is for these other stages. But, of course, if you're looking at it from an economic standpoint, if we put a present value, valuing money at 5% on this heating and cooling bill, and compare it to the construction cost, it's only about 13 to 15% of the construction cost. So clearly in this kind of a case, you're looking to design in energy improvements. You're going to want to do it on an economic basis as well as looking at these heating and cooling energy issues. And the Energy Star program is a program sponsored by DOE, that is working very hard to reduce these energy use numbers in heating and cooling. Here we're just demonstrating a typical house. We can do the same sort of thing for carbon emissions in a representative building life cycle stage. We've added up the emissions, carbon dioxide emissions in construction and demolition. We have to add the emissions from biofuels because they're considered as neutral in that construction stage. We add the emissions from maintenance. Now, we don't draw distinctions in the emissions from maintenance between the wood and the steel house. They're so small because almost all the emissions are driven by the restoration of roofs, and they're common to our two designs. We show the very large emissions from heating and cooling, and we add those up, and that's the subtotal of our sources for emissions. You can see the Minneapolis house has 434 metric tons of emissions, but in this case, now we look at the offsets. The forest sequestration in the floor that's supporting the building of the amount of wood that goes into this house is sequestering 467 tons. That means that just in the forest sequestration alone, we have more stored than we are emitting. Wood product storage adds a little to that. So for our Minneapolis house, you see that the net emissions number is actually negative. We don't see the same result in the steel house, largely because the amount of forest supporting that house is much smaller. So we see a substantially large net emissions number once you include the emissions from heating and cooling. And for our Atlanta house, while the wood house looks substantially better than the concrete house, the difference there is that the southeast forests are on much shorter rotations and don't store nearly as much carbon in the forest. Now, one thing we were not happy about with the life cycle analysis from the standpoint of tracking carbon is it basically provides a cross-sectional profile of all processes. That's a steady state analysis. We think tracking carbon pools over time offers a much more dynamic alternative and perspective. It's also more useful in a financial cost-benefit analysis when there are many years of time taking place. So let's pool our contributions to carbon storage. We'll start with a forest pool. We noted in Pacific Northwest forests they store more carbon than other regions. We see about 29 tons of carbon stored per acre average in the Pacific Northwest on something like a 45-year rotation. If you don't harvest it and let it continue to grow, it will build up to a point before it reaches a steady state, and it's up to about 76 tons per acre if it's not disturbed for 125 years. To develop this kind of data, we basically simulated the growth cycle for each one of our stands, for each one of our management alternatives over time. And the benefit of doing this is by this simulation, we keep very close tracked data of the stand structure, tree by tree. So it's easy to accumulate the carbon pools that are in the forest. This demonstrates an 80-year rotation with two thinning treatments. The lightest green is the carbon stored in the stem, by far the dominant storage. But you can see the very light yellowish green color is the roots. Then we go on to the crown, a little bit of litter. And of course, after every treatment, you're going to see some dead residuals and the fact that they decompose. After our harvest in year 2080, there's a fair amount of dead material residuals that will decompose fairly rapidly over the next cycle. If I compare that long rotation to a 45-year rotation, which is the economic optimum rotation in the Northwest, you can see that if you drew a line through the averages there, that there'd be more carbon stored in the forest on the long rotation than that short rotation on the top. However, you can also see that we did the harvest much sooner on the short rotation. That means we exported carbon into wood products much sooner in the cycle than we do on the long rotation. So our next big carbon pool is the storage in the forest products. Our commercial forest products produce long-lived products stored in the house, in the buildings, and we found about 25 tons per acre average in 120 years. The difference with this and the forest floor carbon, or the carbon in the forest, is that this number is actually growing. It's not steady state. If I look at those carbon pools in the products, the darker area in the center are these long-lived products that go into housing. When the house is completed, of course, that will begin to decay, but at the same time we're producing another crop, and we actually produce the second crop in the second house before, in fact, the first house is removed. In the orange line just below that dark center, you see a decaying function for the chips. We basically assume that the chips supplying paper markets will, in fact, decay over a several decade period. Down at the bottom, you see in the maroon color the manufacturing emissions, and in the much lighter color, almost can't see it, is the harvest emissions. But up on the top in the yellow bar, you see the displacement, or the offset for those purchased energy emissions when we have burned the biofuel and created energy out of it. So basically, it provides most of the energy for the processing energy. So far, we've left out the last stage, and that is every time we produce these products, we substitute for fossil-intensive products. So there is this substitution pool in the market. Now, our long-lived wood products substitute for fossil fuel-intensive products. We estimated 51 tons per acre less carbon emissions from less steel concrete framing in 120 years. And in this case, it's growing quite substantially. I stacked these three pools together. You look at the bottom, draw the trend line through peaks for the forest, the blue line, and it's basically at steady state. I add in the products net of their energy emissions, and it's increasing slowly, but by the time I take the credit for the fossil energy saved every time we produce a wood product that substitutes for steel concrete, you can see the carbon pool is growing rapidly. In fact, in 150 years, it's almost 5 times as high as the carbon stored just in the forest. Now, if we accumulate these carbon numbers over intervals of time, if you look at the intervals over the first 45 years on the left, you can see that it doesn't matter whether we're on a 45-year rotation, 80, 120, or whether we harvest at all. There hasn't been time for the products to get into the products pool or much into the substitution pool except a few thinnings. By the time we get out to 80 years, you can see that the sum of the forest pool in the blue and the products and displacement pool are actually greater for the short rotation than they are for the longer rotations. And in fact, if you go over to the 0 to 165-year interval on the right, you can see that that becomes quite substantial in the amount of carbon stored, being considerably larger for the short rotation than the longer rotations, and especially larger than the no-action alternative of not harvesting. Now, it shouldn't be a giant leap from here to figure out that, well, if short rotations are best, then intensive management will be even better. Here we compare our 45-year base rotation with what's called 45 high-intensive management. It really isn't all that high. It just means some thinnings and fertilization. But you can see as you get out to 80 or 120 years, there definitely is more carbon stored in the high-intensive management case. We stretched it out to 55 years, and you can see a little bit of increased carbon over that 55-year rotation. But the fact is that costs you an awful lot of money. So that carbon is very expensive comparative to the carbon from the intensive management, which is essentially at least a break-even operation and therefore is almost no-cost carbon. You want to accumulate these numbers to get a perspective of how big this number would be. I start with the row that I say is, well, if you ignore the carbon in the products, which is essentially the Kyoto Protocol, I call that the Kyoto error. There's no error in the first 45 years starting from the bare land. By the time you get out to 120 years, you've emitted 26 tons per acre. You accumulate that over the Pacific Northwest private acres, that's some 455 million tons of carbon. That's quite substantial. If I compare my intensive management case with the base case, I can increase the carbon stored in the first 45 years, it'll all be in the forest, by about 7 tons per acre. By the time I get to 120 years, that's up to 14 tons per acre. That stores about 245 million tons. If I compare my no management case to intensive management, this is kind of a best to worst comparison. In the first 45 years, the no management case would be 11 tons per acre less. By the time you get to 120 years, it's 47 tons per acre less, or over 120 years for the private sector of Pacific Northwest, Washington and Oregon West Side, it's about 823 million tons. Gives you some perspective of how these numbers accumulate over a region. Now, we can't leave out the Environmental Performance Index for our Western Washington forests. What we did here is we simulated the impact of the treatment strategies. We used as the criteria, we thought it was the simplest criteria, what are the regulatory objectives? What are they seeking? Well, fundamentally, they're seeking increased late cereal, or what we would call older forests. They're seeking to increase those forests because our management treatments have, in fact, shortened the rotation of forests, and that's where the endangered species emphasis has been. We're also seeking to decrease the stem exclusion structure, which is these overly dense stands. They're overly dense because we've managed them. We've planted them, therefore they're coming back dense, and they generally need to be thinned and would be thinned in a commercial sector if, in fact, it's economic to do so. If I look at my index comparisons across these 3 different rotations of a base case, our intensive management case, and I've inserted a longer rotation case where we've taken some 30% of the private acres and put them on somewhat longer rotations. What you see is there isn't going to be any improvement in the percentage of late cereal structures unless we go to those long rotations. And of course, they're very expensive. However, if you come down in our intensive management case, you can see we are making some improvements in reducing the stem exclusion structures, and especially we're increasing structures that we call reinitiation. These are basically structures that are beginning to take on more complexity. Because we did the thinnings, we're allowing some sunlight in, the structure becomes more complex. It's essentially better young habitat, but it doesn't reach the conditions that we're looking for in older long rotation forests. The other thing, of course, it does is it increases the harvest level under intensive management, and that's going to be a plus for the economic rural communities in particular. Now, I haven't mentioned forest fires. This analysis was primarily done for the west side of Washington and Oregon, where we think the forest fire risk is somewhat lower. However, you should recognize that forest fires release emissions with no savings in fossil fuel, and they also retard the regeneration of the forest. If the fires are hot, like they have been in some of our recent years, they basically will harden the soil and basically slow down any regeneration. So let's summarize some environmental improvement opportunities before we come to some conclusions. We've pretty well shown that the redesign of the house to use less fossil-intensive products would be a good direction to go. We've tended to show greater use of low-valued wood fiber for biofuels. But let's put some more specificity to that kind of idea so that you can see how you would really go about making improvements. I've shown here the Minneapolis wall subassemblies, 3 different versions of them, the total energy, and I've shown the energy contributed by component. Well, what you see here is that the plywood, vinyl, and gypsum are common to all 3 designs. If you look at the percentage increase going from my kiln-dried lumber wall on the right to my steel wall in the middle, you can see a 65% increase in the energy required for the steel wall. Now, one thing we could do is we could increase the biofuel in the lumber. That's demonstrated by going to green lumber on the left. Then the steel is 127% more energy consumption than our green lumber wall, which would be very comparable to a biofuel situation. We're much more interested in fossil fuel than we are total energy. The This chart looks at just the fossil fuel comparison. The steel wall is some 89% higher than the kiln-dried lumber wall, some 135% higher than the green lumber wall when you're looking at the products that in fact are being substituted. So let's be a little bit risky here and extend this analysis to, well, look at the vinyl siding. Look at all the energy in the vinyl siding. Supposing we replace that with a half-inch plywood siding with a good exterior finish. This would be a good challenge for the engineers. We clearly would not be much worse off than vinyl siding, if at all, over the maintenance schedule. Also, we look at the amount of energy in the fiberglass insulation, and we could easily replace that with wood-based insulation. Essentially, recycled paper would come with very low energy implications. And when you get to the gypsum, we could replace that with other kinds of paneling. So the reality is, it would be fairly easy by a number of these kind of product changes to make this substitution difference between the steel wall and this new design substitute wall a substantial difference, much more than what we show by our typical wall section. We look at the global warming potential. Most of those influences walk right through. They get a little bit larger, but the story is very similar. If we look at the air pollution indices, many of those same influences flow through. But when we look at solid waste, it's marching to a different drummer. Here the issue is largely the waste on site. Steel looks very good because it's pre-cut, assembled on site with very little waste. Lumber is traditionally cut on the site, and therefore there is substantially more waste. And gypsum, of course, is cut on site with a very large amount of waste. So if you were to make changes here, it would be in the direction of pre-cutting. If we pre-cut the lumber, we could lower it substantially over what I've shown here, but using our typical substitutions, gypsum was the one that we probably could lower the waste substantially. If I look at my Atlanta wall, you can see the tremendous amount of energy, fossil fuel energy, included in the concrete. It dwarfs even the energy in the vinyl siding, which of course we just showed could be reduced. If I look at the global warming potential, the percentage increase goes up because of the calcification in the concrete. So the suggested alternatives are pretty obvious. Floor assemblies show a somewhat different story. I've shown three different floors here. First thing, if you look at the wood I-joist on the far left, it's substantially more efficient from an energy standpoint, fossil fuel energy standpoint, than the wood dimension joist. That's because you're using much less lumber in a wood I-joist than you are in dimension lumber. If I look at the steel joist, however, you find that it's much, much larger than you might have guessed when you look back at that wall assembly. The steel wall is quite efficient. It's only a little bit higher than the lumber wall. And that's because, first of all, our Minneapolis house only uses essentially 2x4 sized steel studs. It uses 2x6 studs for lumber in order to contain the insulation to meet the R code. Steel put EPS insulation on the outside to make up the difference, but as a consequence, got to use a lighter gauge steel. The minute you go to floor joist, you have the bending effect involved, and you have to use much higher gauge steel to get the same kind of performance in the floor. As a consequence, while steel was quite efficient in the wall use, very inefficient in the floor use. And of course, if you go to the global warming potential numbers, the percentages look even worse. So that gives you some perspective on how you would go about looking for improvement opportunities from a product change standpoint and from a process change standpoint, such as biofuels. Now, if the environmental pollution control improvements used LCI data, I can pretty well assure you that we would be using more biofuels. That is to say, the pollution coming from using biofuels, which does run into the pollution control standards, is probably far less polluting on an overall LCI database or on LCI analysis. So as a consequence, we really need to be looking at pollution controls from a much more systematic life cycle inventory analysis standpoint. And we pointed out that there were substantial improvements in more intensive forest management. We just can concentrate on those for the moment. We want more intensive forest management. That'll give us both more wood per acre. It'll also give us more solid wood, and it, of course, produces more carbon stored. But we want it in solid wood production. We don't want it in longer rotations. If you want it for longer rotations, that's for other reasons. Even small carbon incentives, such as carbon credits for additionality, meaning intensive management, would go a long way because we aren't intensively managing a lot of the acres today. If we need long rotations for better biodiversity, we in the beginning thought that that would be complementary to stored carbon, and of course we found out that short rotations were best. So in fact, biodiversity is not a complement to stored carbon, and in fact, if it's needed, it has to be purchased separately, and of course it costs a fair amount of money. Now let me go through the take-home messages. In conclusion, we can assess the environmental performance of products and buildings. Guessing can't. We see a lot of errors by the criteria that other people have used by assuming what the impacts are. We've noted that there are many potential improvements by using less fossil-intensive products and more wood products. Energy for heat production remains the driving factor in the wood processing energy. Most of that could be bioenergy. It would take some incentives for green energy credits, or just higher natural gas prices would get us there. Short rotations with intensive management store the most carbon across all stages of processing. So we don't want to use wood for energy if, in fact, we can get it in long-lived products. Wood used in long-lived products that provides the greatest reduction in fossil fuel use and emissions. And I noted that forest fires are going to reduce carbon storage. That's a lost opportunity to reduce fossil fuel uses. I must acknowledge the support for this kind of research. It has all been done through the Consortium for Research on Renewable Industrial Materials. The 15 research institutions, there's some 23 authors on the final report. DOE and 5 companies funded the original research plan. The U.S. Forest Service Forest Products Lab, 10 companies and about 8 institutions funded phase 1. We couldn't have done this kind of work without the support of product manufacturers to get into their facilities, survey the results, ask questions when we found that we didn't understand some aspects of the data. We did get a little bit of support from the National Research Initiative Competitive Grants Program, and similarly from some special grants from EPA to do the carbon links to forest management. I want to close with just a few words on where we're taking the research for our next phase. In phase 2, we're going to extend the forest resource life cycle inventories to the inland west region, where fires are very important, and also to the northeast, north central, including both softwoods and hardwoods. Our product life cycle inventories will include these 2 regions, but they'll also include medium density fiberboard and particle board, and we think we need to do a better job on resins because they're so important to these products. They're not structural products, but they are large volume products, so they will have a substantial impact, and they do have long lives. We're going to do more work on the building components. You've seen a preview of that in this presentation where we look right down into the different subassemblies on how you would build these subassemblies differently to get better performance. We're actually going to try to make the life cycle inventory and life cycle analysis data easier for people to use, that they don't have to be quite so expertise to understand what's going on. And we are going to look at different kind of residential construction alternatives. Certainly a townhouse, and we want to cover a broader geographical range than just Atlanta and Minneapolis. So overall, we're going for a more full geographic coverage for high volume products and more end uses. Wood products are not very homogeneous from region to region. That's why we have to do this analysis on a regional basis. Now, if that's not enough detail for you, I'd suggest you go to our website, www.corum.org, The complete Phase 1 report, I've never counted the pages, it's some 800 pages, is there. We have a 12-page summary up there, which was published in the Forest Products Journal. We produced a 4-page fact sheet for people that can't handle much more than about 4 pages, and we have a number of 1-page releases up there if 1 page is about all you can handle. We also refer to the Athena website, which is the model that helps you as an architect design buildings and be able to track all of these environmental impacts, and the Landscape Management System website, which we used for carbon tracking starting in the forest floor. And all this data hopefully will, over the next few years, be assembled in this US LCI database managed by NREL. There is data up on this site already, but the data will become much more complete and comprehensive as more data is provided and properly reviewed. And I thank you.